All right, well, good morning. It is Thursday, February the 18th, here at Spain Park, AP Chemistry. So for those of you at home, for the first 20 minutes of class today, we've worked on page 664, problems number 32 and 36. So I highly recommend that you get your book and go ahead and try to work those problems. Just pause the video, work those problems before I go over them, okay? So, number 32. Number 32 says gaseous hydrogen iodide is placed in a closed container at 425 where it partially decomposes. Partially decomposes. That's telling me it doesn't go all the way to completion. That means that it's a reversible reaction. We're going to be in equilibrium because only part of it's going to react and then it's going to go back and forth. And then at equilibrium, that's huge for it to say that. Because now I know that those are my equilibrium concentrations. Kc, Kp is always equilibrium concentrations, not initial concentrations. All right, so those are kind of key words we're looking for in this. So what's my Kc? Since it's given in molarity, I want the value of Kc. So what's my equilibrium expression simply going to be? What's the equilibrium expression going to be? Somebody. Go ahead. So.
Concentration of H2 times the concentration of I2 over the concentration of HI to the second power.
To the second power. Okay? So if I need to know Kc, I have to know these three values. Well, this is the easiest of all types of problems because they just give me all three values. So then it's just plug and chug, just stick the values in there. The hydrogen is 4.79 times 10 to the minus fourth. The iodine is 4.79, so I can just square that, divided by 3.53 times 10 to the minus third squared. And all of that turns out to equal, you gotta say it louder. 0.0184. And there really would be no units on that because it's going to be molarity squared divided by molarity squared, but we don't ever really have to worry about units on K. That's the easiest and simplest of all. We have to know how to write our equilibrium expression, but then we just kind of plug everything in. All right? Then we go to number 36. So now we have a very similar reaction. H2 plus Br2 goes to 2HBr, just substituted in bromine for iodine. At equilibrium, a mixture of this and this is heated in a 2-liter vessel. So now we're not at equilibrium. Now we're saying, okay, we put this much in. That's my initial amounts I'm putting in. Then it says, at equilibrium, it contains this much hydrogen. Okay? So this is where I have to make my ice table. So I have H2 plus Br2 goes to 2HBr. Now a lot of teachers have you do a whole separate table, you know, and just kind of write everything down. I kind of like just kind of building it around the equation. It's up to you as far as how you want to do that. But I tend to just do my initial at the start, the change, and my equilibrium. That's ice. Initial, change, equilibrium. A lot of teachers actually call them rice tables because they put in the R for reaction. You write the reaction, initial, change, equilibrium. So you'll see it either way, an ice table or a rice table, but this is the reaction part of the rice table. And then a lot of them just separate this down as a completely separate, thing. So, what do I have to do with these grams? Got to convert to moles. So, H2 is going to equal 1.374 grams divided by,
2.02.
since there's 4 sig figs here, let's use 4 sig fig, so it'll be 2.016. Don't ever let your molar mass be the sig fig limiter. Divided by what? 2 liters. Okay, and what does that come out to? Kevin, you've got to be loud enough for me to hear.
I got 0.6802.
0.6802. Did anybody agree with that?
That's without dividing
Yeah.
2 liters, so.
Oh, yeah, sorry, it's moles and then, yeah.
Say that again, Anna.
I think it's 0.340.
340. Do we agree with that number? Yes. Okay, so I do the same thing now for the bromine. It's gonna equal 70.31. Divided by the molar mass, it's 79.90, I believe, 79.90, so it's gonna be 159.8. Divided again by the 2 liters, and that comes out to equal,
0.21995.
so 220, if you round it to 3. Okay, now, so that's my initial concentrations. Let's do that in a different color. So my initial hydrogen is 0.340. My initial bromine is 0.220. And there's 0 of that initially. Now, I go through and it tells me that at equilibrium I have this much hydrogen left. So I gotta convert this into molarity. So this is going to be initial. And then H2 at equilibrium is gonna equal 0.566 grams divided by 2.016 grams per mole divided by 2. What's all that equal? Did nobody did that part?
0.140.
0.140. So that's my equilibrium concentration of this, 0.140. So what does that mean my changes? 0.2, right? It goes from 0.34 down to 0.14. So it's going to be minus 0.200 molar. So what's this going to be? Minus 0.200 molar. So at equilibrium, 0.220 minus 0.20 is going to equal 0.20 molar. It's all that's left at equilibrium. And then lastly, I started with 0. What's this going to be? Plus 0.4. How do I know it's plus 0.4? For every one of these, you're going to get 2 of those. That's the stoichiometries, the coefficients. Okay, is everybody seeing that? So now I know it's 0, so this is my 0.4 molar. Now, all of that was necessary to get to the exact same point we were on problem number 32. Now we have all of our equilibrium concentrations. Now we just plug it into the equilibrium expression. Kc is equal to HBr squared over H2 times Br2. And so we end up getting 0.4 squared divided by 0.14 times 0.020. And we get on that, we get, say that again, 0.0229. That's my value of Kc. And since it's 0.02, what does that mean? Is it going to be more reactants or more products? What's it a ratio of? Products over reactants. And since it's less than 1, which is the numerator denominator bigger? the denominator, which means we have more reactants than we do products. If K is less than 1, it's reactant favored. K is greater than 1, it's product favored. That's what K is telling us. Where is the equilibrium lying? Because the equilibrium, again, does not mean equal amounts. It means the forward rate and the reverse rate. It just depends upon when it reaches equilibrium, how much product got made. A big value of K, oh, you got a different number?
57. I got 57.
Okay, well, if you got a different number, then you have to speak up.
Well, I
You'd
just
be
did.
wrong.
Yeah.
Okay, so it came out to 57 instead of 0.14?
57.1.
Okay. Oh, not that one. This. So it's all set up right, it's just 57.1. So now that it's greater than 1, what does that mean? It'd be product favored. Okay?
I don't know how we got that first number.
Oh, my calculator, I swear.
It's my calculator. I put it in all right. It's my calculator's fault. That's right.
No,
I used to
really-
try to blame that stupid computer, but it always comes out to user error.
I accidentally somehow multiplied it by 0.02.
Oh.
I don't really know how that works though.
Well, what happens is if you go 0.4 squared divided by 0.14 times 0.02 without a parenthesis, your calculator gets an answer for this value and then multiplies that whole answer by 0.02 rather than dividing it in. So all you gotta do is you can do two ways. 0.4 squared divided by 0.14 divided by 0.02, or 0.4 squared divided by parenthesis 0.14 times 0.02, close the parenthesis, equals. Because you got to get your calculator to know the order of operations. Okay, that's a common calculator mistake. All right, so these are our first two types of problems. When you're given initial concentration, we have to use ice tables here. And on this one, we're about to do that. On this one, we're going to use ice tables as well. Okay? This one here is given to you. You don't have to figure out any concentrations. But these two, you're going to be given an initial. You just have to use the stoichiometry, the balanced equation, and figure out what am I starting with, what's my change, how much do I have at equilibrium. And they're generally going to give you initial concentrations and then one equilibrium concentration from that, and then you just set up your table. Does everybody understand where all these numbers come from? Okay, we're all good? Okay, so let's look at the third type of problem. This is what we were at the very end of class yesterday. I alluded to the packet that I just gave to you. And we look at 1988. That's 83. 1988. Okay, so at elevated temperatures, antimony pentachloride decomposes into antimony trichloride and chlorine gas, as shown by the following equation. An 89.7 gram sample of antimony pentachloride, SbCl5, they give you the molecular weight, is placed into an evacuated 15-liter container. Why do they say evacuated 15 liter? What's the word evacuated? What's that telling us? There's nothing else in there. So that's the only thing. So you don't have to worry about air, you don't have to worry about, anything else. Almost every single problem is going to say that, and that's just implying nothing else there. Okay? So, a lot of times they get so wordy in these problems, we don't know what all the words mean, and so it kind of throws us for a loop. So I always try to make sure we understand what each thing's telling us. So we want the concentration in moles per liter of SbCl5. Well, that's gonna be pretty easy. SbCl5. How do I get the concentration given this, and that? No, not even stoichiometry, simpler than that. Stoichiometry has a balanced equation, the ratio. This is just gonna be what divided by what divided by what? 89.7 grams divided by 299 grams per mole divided by 15 liters. Okay, advice is all that being seen. Okay, what do we get? 0.020. Are we agreeing with that on the back row? Okay, 0.020 molar. Okay, so that's just a simple question of, do I know how to calculate concentration? So they're asking, they're going to be graduating in difficulty here, but they're just saying, okay, solutions, I have this. Do you know how to calculate molarity? Pretty simple calculation. That's going to be a 1 point, problem. Now, this is very, very common. What is the pressure in atmospheres before any decomposition? So the pressure in atmospheres. I'm given a temperature, I'm given a volume of a gas. I now know kind of moles of gas. So how do I find pressure? Ideal gas law, Pivner. Okay? Very rarely is there going to be a gas law problem. They just always throw this in. If you saw, they had it in the kinetics problems, they had to calculate through the gases. Thermo problems, they had just a first section, what would be the pressure. So this is how they're going to do gases, and it's almost always the ideal gas law, P equals nRT. Now, let me just kind of show you a rearrangement here. If PV equals nRT, well then pressure is equal to N over V RT, right? Well, N over V, moles per liter, is molarity, so another rearrangement is pressure is equal to Merton, MRT. Now, you could very easily keep it in this form and know that we had this many moles, this many liters, and just plug those numbers in. But we already did that, so it's just a shortcut using the 0.02. So it's going to be 0.020 times 0.0821 times the temperature is 182 and 273 by 455 K.
Oh, did they give you the constant 0.0821?
Yes.
Okay.
And the other one, the 62.36, and then there's one in thermo that we used. It was the 8 point. Well, we never really used it because that's I'll show you when we use that one.
Okay.
Because that's going to be in the equation. I remember some of the problems said calculate the equilibrium constant from delta G.
Mm-hmm.
Since we hadn't done K yet, we couldn't do that, but it's just plugging into a formula. But you use a different value of R for that,
Okay.
but it's given as well. So what does all this equal? 0.75 atmospheres. Okay? So, none of this is really an equilibrium problem. This is just kind of leading up to it. This is just kind of testing other things leading into the problem, just related to the problem, but testing, do you know ideal gas law? Do you know how to calculate concentration? But I do know now that my initial concentration here is 0.020. And we didn't put anything of this into there. So my change in an equilibrium, if the SbCl5 now is 29.2% decomposed when equilibrium is established, calculate the value for either Kp or Kc. So we could start with Kc here, or we could start with Kp here. I always like Kc better than Kp. I don't know why, I just tend to go that way. But you can do it either way. This would be your initial pressure. This is your initial concentration. Either one. Let's do Kc. So, what do I do? How do I find what my change is?
Take 29.2% of 0.02 more.
Okay? And that's gonna tell me what? The changes, how much decomposed. This is 29.2% decomposed. That's how much actually reacted. So it's going to be, now remember, when you multiply by percent, what do you have to do? The decimal is going to be 0.292. So 0.292 times 0.020 molar. So my change is going to be,
I got 0.00584.
0.00584 molar. So when you're given percent decomposition, that's just telling me what my change is. So now so since that's a minus, what are these gonna be? Plus the same amount. So at equilibrium, when I subtract that, well, I'm gonna get 0.0142. And then obviously 0.00584, 0.00584. Now, I'm doing this on a test, I'm doing this on the AP test. I don't bother to write this 0 plus, because that's intuitively obvious that it's that. But, I mean, you can if you want to, but you just don't need to, you know, you can save time and just leave it there, and not have to write it out. Saying that mainly for the guys that like to do as minimal amount of work as possible. Okay? So, now what do I do with that? Now I find Kc. Now I have my equilibrium concentrations. Now everything is the same. I just do Kc is equal to, I'm not even going to write the expression because we know the expression, 0.00584. It's going to be squared because it's going to be this times that divided by 0.0142. And Reagan, what you get?
0.00240.
240. And again, we don't worry about units. Do we all get that? Okay. All right, so these are ways of calculating K from concentration data. Okay, add that. Okay, from concentration data. You're either going to be given them all. You're given one. This is the most common, probably, given one. Given the initial and one equilibrium, and you set up your ice table and figure it out like we did there on 32, or you're just given a percent decomposed. So let's just do one more percent decomposed. I'm going to let you guys do that, and that's going to be 2008 in this packet. 2008. Notice the setup on this one. We have arsenic pentafluoride. What did we have in the previous problem? Antimony, add bud. Antimony, arsenic. Exact same thing, they just changed elements in the same family. They all bond the same way, they all react in the same way. Okay, so back here. So now, when I'm looking at this problem, exact same reaction except it's antimony versus, it's arsenic versus antimony. A 55.8 is into a evacuated 10.5 liters. It's like they just changed the compound and changed a few of the numbers. What's the initial molar concentration? What's the initial pressure? In terms of molecular, write the equilibrium constant, and then when this much percent decomposed, calculate the equilibrium concentrations. So let's just see if you can go through and just do that whole problem. Those of you watching the video at home, this worksheet is posted in Classroom. And we haven't talked about D much, but see if you can figure it out. Really?
Zach Swally, please from the front desk.
That would
My
be your
brother.
Brand Aaron, please from the front desk.
Once again, it's real important that you ask questions if there's something you don't understand on this, because I'm not going to give you homework problems on these. This is your chance to know whether or not you know how to do these problems. Okay? So it's okay to not get it on the very first try. Okay, let's look at this. You should be, if you're not finished, you should be well on your way. So we want to do the initial molar concentration. So that's going to be the exact same thing that we just did on the previous one. ASF5 is going to equal 55.8 grams. Now they don't give you the molar mass on this one, but we all know how to calculate the molar mass. 1 arsenic, 5 fluoride, fluorines, and we end up getting what's the molar mass? Any-
My bad. 169.92 is what I.
169.92 grams per mole. Divide that all by the 10.5 liters, and we end up getting 313 molar. If you want to, you can say SB, not SB, ASF5. Okay? Then it says, what's the initial pressure? So I got it. We're gonna go PV equals NRT.
You heard him, straight from the horse's mouth. Can I see the student? Oh.
Do you know that Miss Cash sat right there, okay, in this class in year 2001, 2002?
When I was a junior.
When you were a junior. in
It was 2002, 2003.
3. Always had a smile on her face, came in, just loved learning.
Still did.
She is the ideal chemistry student, I'm just telling you.
I didn't take AP though.
Okay?
I was the light of his regular chemistry.
That's
class.
right. And so, and then there was this guy,
Devontae.
there was this guy that
Oh,
sat.
Nick? Nick wasn't in that class.
He wasn't?
He wasn't in my class, I didn't know him. He might have been in our class, but I didn't know him. You know what's funny? Is I like to show my students the yearbook. And I always point out my husband, you've seen it.
Yeah.
He had a glow up, didn't he?
You really did.
He had a glow up. You know what a glow up is, don't you?
In other words, he started looking better.
He started looking better.
I had it gloved down.
No! Anyway, he doesn't teach regular chemistry anymore.
Anyway, she sat right there. Nick sat way in the back. Did not generally have a whole lot to say in class and was not all that interested in learning chemistry.
He does good now, though.
I'm sure, I know, that's called growing up and maturing. All right,
Oh, there's my camera.
all right. She just makes me smile every time I see her in the hallway. Just, I always remember seeing her right there. But she was row wetter then, didn't have row wetter. Anyway, that's the another 10, 20 years from now, I'll be talking about y'all just sitting right here. I remember that Mike, he sat right there. I made him work the camera and he got all confused. All right, so the pressure, we can again say pressure, and we can just shortcut it to MRT. Is equal to 0.0313 times 0.0821 times the temperature, which is 105 plus 273. That's 378. So what does that pressure turn out to be? 0.971 atmospheres. Okay? So, now we have this. So in terms of molar concentrations, write the equilibrium concentration. So in terms of molar concentrations, what are they saying? What do they want you to write? KC, not KP. All right? So just make sure we're reading everything carefully. So we know that KC is going to equal ASF3, F2, all over ASF5. That's all you have to write for that. That's an easy point. Even if you can't do these, you can get a point for that. Okay? So do whatever you can, because we're on a point scavenger hunt on the AP test. You need to get 75 points for a 5 out of 100. Okay? You don't have to know them all. Okay? But to get a 5, you got to know 3/4 of them. So, got to get them when we can. So when equilibrium is established, 27.7% of the original number of moles of ASF5 have decomposed. Well, I know that my initial here now is 0.0313. This is 0 and 0. So my change, equilibrium, how do I get my change? 0.277 times, and that's gonna equal,
0.00867.
so this is gonna be minus 0.00867. This is going to be plus 0.00867 plus 0.00867. So then the question is here, calculate the molar concentration of the ASF5. So all we have to do is subtract, and what does that come out to?
0.0226.
Okay, so that's your answer to C1. Okay, and I mean, even if you have on your ICE table, if you just show this and then put your answer, that's significant work. Okay, because as an AP reader, we look at everything on the sheet to see, you know, what do you know, what do you don't know, did you show how you got from point A to point B. This is definitely showing how you got from point A to point B, so you just put that there. So now it says then calculate KC. So I'm going to come over here. We already have our values, okay? So it's going to be 0.00867 squared divided by 0.0226. And what does that equal?
0.01635.
Okay? Do we agree with that number? I'm not seeing a lot of agreement on the back row.
I got 0.00333. I think it's like
That's what I got.
half of that, or twice that.
Okay? That's why we have to agree. Okay, so Reagan, say it again.
0.00333.
Do we agree on that number? Okay. You guys got to speak up. You just got to give me, I didn't get that, okay? It doesn't mean that you're wrong. You know, we'll just see.
It means that I'm wrong.
That's what that one meant, okay? It's just, again, but those of you that are doing this, make sure we're practicing putting everything in our calculator. So, I mean, we don't make a silly mistake and have it all set up right, but we don't put it in our calculator correctly and you miss your point. Okay, so it's a 1 point. Even if you have it set up right, you don't have the right answer, you don't get your point. Okay? Now, what is mole fraction? It says, what's the mole fraction of F2? The part over the total. Okay? It's going to be part moles over the total moles. Now, correct me if I'm wrong on this mathematically. To get moles, we multiply this by 10.5.
Yeah.
We multiply this by 10.5. We multiply that by 10.5. Then you take the mole ratio, you take the part over the total number of moles. However, since we're multiplying everything by 10.5, should be the same ratio if we just do it in terms of molarity. Okay? Did you multiply it out and divide everything? Okay, so you have your answer. So let's just see if molarity works out. I should know these things, but I don't. So X, this stands for mole fraction. Capital X is how they represent mole fraction. The mole fraction of F2, we're going to take the molarity at equilibrium, 0.00867, divided by the total molarity, which is going to be 2 times 0.00867 plus 0.0226. And it's just a fraction, so we don't multiply. It's not a percent. We just leave it as the fraction. And if you're going to do this on your calculator, you probably want to have another set of parentheses. We get an answer?
0.217.
0.217. Is that the same as what you got, just doing it in terms of moles?
I think it's like half of what I got. Cause I got 4.4,
Hmm,
or 0.044.
okay,
Wait,
well,
I might have done.
well, let's just double check. I don't wanna teach y'all something wrong. What do those two numbers come out to? Does everybody know why I'm doing this? Molarity times volume equals moles. Okay? Molarity times volume equals moles. Moles per liter times liters equals moles. So I'm taking the given equilibrium molarities, multiplying by the 10.5 liters,
Top one is 0.237.
237. And the bottom one's gonna be,
0.0910.
okay? So then again, our mole fraction of fluorine here is going to be moles of fluorine, which is gonna be this one, divided by 2 times 0.01910 plus 0.237.
It's right. It's 217.
It's 0.217?
Yeah, I just messed up the first one.
Okay. I thought it would be because we're multiplying everything by 10.5, therefore the ratio of everything should still be the same. So the point I'm trying to make on that, and I just wanted to confirm it, is that if mole fraction on this one, you could leave it in molarity and just do molarity of the fluorine divided by total molarity, because it's gonna be the same ratio because it's all in 10.5 liters. Mathematically, that should be the same thing. So just a shortcut so we didn't have to do this step. Okay, now, better safe than sorry. That's not a big step. Okay? Go from there. Are y'all comfortable with these three types of problems? Okay? Especially just A, B, and C, 1 and 2 on this one. Okay, D was kind of something we haven't talked a whole lot about, mole fraction, but mole fraction is just part of the whole, so it's not that challenging of a concept. All right, so now what we want to do in the remaining few minutes is go the other way. If we're given the value of K, how can we find our equilibrium concentrations? I can see the excitement all over y'all's faces that you want to learn this. So this is going to be calculating equilibrium concentrations given initial concentrations, pressures, and Kc or Kp. Let's see if there's one on here before I go to the book. Okay, I'm on page 665 if you happen to want to follow along, but I'm going to be showing it up here. start with number 54. So first off, that's a solid. So what's my KC expression going to be? Not plus, just Steve, you don't need. It's just gonna be NH3 times the H2S. There's no denominator because it's a solid. Only aqueous and gases go into our equilibrium expression. We just totally ignore solids and liquids. Okay? So, calculate the equilibrium concentration of NH3 and H2S if a sample of solid, whatever that is, NH4SH, is placed in a closed vessel at 218 and decomposes until equilibrium is established. So in other words, it's not going to go all the way. But we do know that Kc, all of this is going to equal 1.2 times 10 to the minus 4. So, I'm putting in, notice they didn't even say how much of this they put in because it doesn't matter because there's still going to be some solid at the bottom. We don't need to know its concentration. But initially we have 0 and 0 of that, right? We do change in equilibrium. We don't know the change. It doesn't tell us anything about the change. This is why we learn algebra. We're going to let the change equal x plus x plus x. So at equilibrium, I'm going to have x amount of this and I'm going to have x amount of that. And it's going to be 1 to 1 because it's 1 to 1. So all I'm going to do is I'm going to say is equal to x times x. So I take the square root, x equals NH3 equals H2S equals the square root 1.2 times 10 to the minus 4th, and that equals 0.0110 molar. So that would be my equilibrium concentrations of both. So the equilibrium, when I have K, I can figure out what the equilibrium concentration is going to be. Let's look at one a little bit more complicated. Let's find one a little more complicated. I need glasses on to find one more complicated. Okay, so we're going to look at number 77. Okay? So, we're given that's equilibrium. Notice gas, gas, gas. Kp is given. If 0.025 atmospheres of IBR is placed in a 2-liter, what is the partial pressure of all substances after equilibrium is reached? So the only thing I know is my initial pressure is 0.025 atmospheres. 0 and 0. But I know Kp is that. Now again, the temperature's given, but it's only given because every equilibrium constant is dependent upon temperature. The only way you're going to change the value of K is change temperature. Changing concentrations, changing pressures does not change the value of K. So, what I'm going to do here then is I have to look at my change in equilibrium. Now because this is 0 and 0, what's the only way the reaction can go to reach equilibrium? Forward. So we're gonna say this is, what do you think we're gonna put here? Minus what?
Minus 2x.
2x, because of the 2. So we're gonna say minus 2x. This is gonna be plus x and plus x. So at equilibrium, we're gonna have 0.025 minus 2x, x, and x. So in our equilibrium expression, Kp, it's going to equal the pressure of the iodine times the pressure of the bromine divided by the pressure of the IBR squared. It's going to equal x times x divided by 0.025 minus x squared. And all that's going to equal what? .5 times 10 to the minus third, the given value of Kp. Now, fancy calculators, you just plug that in. Now, just so you know, you're never going to have to use a fancy calculator on the AP test. Okay? Somebody tell me mathematically, how can we simplify this?
Get rid of the denominator by multiplying it.
Okay? But you're still going to have the squares in it. If I take the square root of both sides, I'm going to get x over 0.025 minus x is equal to the square root of this, right? Yes, ma'am.
Shouldn't it be minus 2x squared?
Yes, it should be minus 2x. Sorry. Thank you for not letting me go all the way through the problem and not having that. Okay? I wrote it right there. Just didn't translate it to there. So, take the square root of both sides. And we end up getting x over 0.025 minus 2x is equal to the square root. What is the square root of 8.5 times 10 to the minus 3?
0.092.
0.092. Okay, now can we do the algebra from this point? Okay, now Nathan, what do we need to do?
Now you multiply the denominator.
This has to come up here, right? Equals x. So when you have this, what property do we have to use to make sure the distributive property? Ooh, this is why we learn math. So we can do this kind of stuff. Okay? Learning the distributive property in math all on its own is not very, exciting or worth anything. But when you can apply it into a real situation, now we're talking.
Makes it so much more.
Makes it so much more, hey, this is why I'm in math class. So I can do better in science. It's just, anyway. So we're gonna, x is gonna equal 0.092 times 0.025 minus 0.092 times negative 2x. So I need some numbers. What is this term?
It wouldn't be negative 2x, because you already have the negative in the.
So you have 0, 0, 2, 3. You have too many negatives, so.
I have the 0.02 times there.
But you're.
Oh,
It'd be a-
okay, gotcha. Okay, so what do we get? I need this term and I need that term.
First one's 0.0023, and then minus 0.184x.
Okay, so then I have to collect my like terms, bring that over here, so I'm gonna have 1.184 x is equal to 0.0023. Divide both sides by 1.184. X is equal to
0.00194.
Say that one more time.
0.00194.
194. And that's going to be my equilibrium pressure. That's what X is, so this is going to be atmospheres, which is equal to the pressure of my I2 is equal to the pressure of the BR2. How would I get the pressure of the IBR?
Subtract, that times 2.
I just got to solve for this, right? I know what X is now, so then .025 minus 2 times 0.00194. And that equals, it's not IV concentration, it's the pressure. Sorry. And our final answer is
0.0211.
okay, so we have our answers is all right here. So when you're given your initial concentration and the value of Kc or Kp, you have to set up your ice table, but you have to include X's. Okay? Because we don't know, but the X's follow the coefficients, okay? And we just kind of go from there. And then you just solve for it. Now, if you end up with a quadratic equation, most of the time they just ask you to set it up. Okay? You're not ever gonna, because not everybody can have a programmable calculator that has the solve function in it that you could just plug that into and solve for it. They're not gonna make you do the quadratic equation, okay? This is taking the square root of both sides is a trick, so if it's a perfect square, we can do that. But you're never gonna have to do quadratic equation.
In this case, you lost the negative x value, but like, cause like when you square rooted it, you lost.
Yeah, you just, cause that's not a logical
But
answer.
what if there's like a situation where,
It won't be. Number two, you're not gonna have to do, what will happen is if you get two positives, but when you do the subtraction, you'll end up with a negative here.
okay,
And so it won't be a valid answer either. Because you can't have a negative amount of a substance. But again, generally, you're not gonna have to do that, on my test or the AP test. Okay? Now, the perfect square, you may have to do. We just take the square root of both sides, that gets rid of the square, then it's just algebra. Let's see, we just did which one? That one?
yeah.
What is this one? We're not ready to go there yet. Trying to find another good one. That was a simple one. Crud. Let me go back to my binder. I know I came from. Okay, see what you can do on this one. I'll give you a hint. This time they kind of give you what X is. Kind of. What's my K, since they've given pressure, what's the KP expression gonna equal? KP is gonna, which is equal to, they tell you the value, 0.133, is equal to what?
Pressure of
Squared divided by pressure of N2O4. Okay? What's the only thing we don't know?
pressure of NO2.
The pressure of the NO2. So this is gonna equal the pressure of the NO2 squared divided by 2.71. Okay? So then, You just multiply 2.71 times 0.133. Is equal to the pressure of the NO2 squared. Multiply that and take the square root. That's all we need to do. Set up the problem. What am I given? What do I need to know?
I did an ice table first.
But you don't know what any of the initial is. That's why we can't necessarily do an ice table.
Alright, but if it was, since it's 2, like would it be 2x squared?
Well, it
Is
would
that
be
gonna
2x if we let x equal this. But because we don't need this as a variable, we can just let this be the x, the pressure of the NO2 squared.
Okay, I got you.
Okay? The only reason we did the x and the 2x is because we let x equal the 1, and then with the coefficient of 2 is going to be 2x. Okay? So this is just one where you're given Kp, you're given one of the reactant constant pressures, you just got to find the other one. Okay? So if we look at one other one. What do we get, by the way?
0.6004.
Okay, 0.6. Everybody knows, you multiply this, you gotta take the square root. All right, uno más. No. That's all, though, that last word is flask. Okay, so carbon monoxide reacts with steam to produce carbon dioxide and hydrogen gas. Okay, and that's balanced as is, a 1 to 1 to 1 to 1. They tell you the equilibrium constant. Calculate equilibrium concentration, so that makes that Kc. You have all your concentrations of all species. If 1 mole of each compound is mixed, hold on. Okay, so we're going to put 1 mole in. It's going to be 1 molar, 1 molar, 1 molar, and 1 molar. So what we need to know is what direction is the equilibrium going to go. Okay? But if I just do my Kc, it's pretty simple. What's Kc? What would it equal if I just plugged all these values in? 1, right? 1 times 1 divided by 1 times 1. So the equilibrium constant is 5. So in order to reach equilibrium, what do we have to do? Make more product or make more reactant?
Product.
Make more products, right? So we know the reaction is going to go to the right. Now that's going to be tomorrow's discussion on how we really calculate that. It's going to be calculating the value of Q, the reaction quotient, and then that's going to tell us where we're going to go. But for right now, I'm just telling you, this is going to go to the right. So what does that mean in terms of X? Is this going to be minus or plus? And that's going to be plus, okay? So go from there. Okay, so that's my equilibrium expression. Okay, products over reactants. I know that it's gonna be this times this, so it's gonna be this squared divided by this squared. Does everybody understand how I'm getting that? You know, that it's gonna be that times that, so it's just gonna be squared, divided by this times this is gonna be squared. So take the square root of both sides. What's the square root of 5.1?
2.26.
2.2 what?
6.
6 is equal to 1 plus x over 1 minus x. Okay, so we have to multiply over here, so it's going to be 2.26 minus 2.26. X is equal to 1 plus x. Add that over there, subtract this. 1.26 is equal to 3.26 x. X equals
0.387.
point what?
387.
387. Okay, now that is not my answer. Because what's the question asked for? The concentration of all species. So we have to do this part. So the concentration of the CO, which is going to equal the concentration of H2O, is going to equal 1 minus 0.387 is going to equal 0.613. Okay? Whereas the CO2 is going to equal the H2 is going to equal 1.000 plus 0.387. This math is a little bit easier, 1.387 molar. Now, what we have just done here is called a Q problem. Q is what we call the reaction quotient. You calculate it just like you calculate K. Products over reactants, coefficients, raised to powers. The only difference is Q doesn't have to be at equilibrium. So we use Q to determine which way the reaction is going to go to reach equilibrium. If Q is less than the given K, then we need more products and it's going to go to the right. If Q is greater than K, that means we have too much product, it's going to have to come back to reactants in order to be able to reach equilibrium. It just tells us the direction the reaction is going to go. That's what we're going to look at tomorrow, are these Q-type problems. But the problem with the Q problem is that they never use the letter Q and you don't know it's a Q problem. You have to figure that out. But that will be our fun Friday activity. All right, well, I hope you guys have a great rest of the day and go Jags.